In this video, I will test hypothesis for population proportion using Ztest. So far we have discussed many aspects, the procedure of testing hypothesis for population mean when sample size is large, but in many real world situations in business and other areas where collected data are in the form of counts or the collected data are classified into category or groups according to an attribute or a characteristics. For example, the peoples living in a colony may be classified into two groups such as male and female with respect to the characteristic sex. Also, the patients in a hospital may be classified into two groups as cancer and non-cancer patients, and the lot of articles may be classified as defective and non-defective, etc. Like this, we can categorize any attributes or characteristics into two groups. Here, collected data are available in dichotomous or binary outcomes, which is a special case of nominal scale, and the data categorized into two mutually exclusive and exhaustive classes, generally known as success and failure outcomes, where we can define any attribute as two groups such as defective or non-defective, success or failure. In such cases, we have to focus such cases very specially, that is using population proportion. For example, the characteristics sex can be measured as success if male and failure is female or vice versa. So such situation of proportion is suitable measure to apply. So in all the situation I quoted just now, we required a test for testing a hypothesis about the population proportion. So it is a very special case in testing hypothesis, whether it is Ztest, t-test or whatever the test we test. So proportion, the category, the attributes that are divided into two groups can be treated under population proportion. In this video, I will address population proportion in Ztest. So let us moving further. In population proportion, before you moving further, you have to check the normality condition in population proportion. Unless meeting a normality condition, we are not able to move further. So while you are checking normality condition, there can be arise two cases. That is case 1, when sample size is not sufficiently large, that is either of the condition NP, N means number of sample size, P is sample proportion must be greater than 5, or NQ must be greater than 5. If this condition does not met means, then we use exact binomial test. But exact binomial test is beyond the scope of this category. We have to address that in a separately. So one thing is clear, when sample size is not sufficiently large means the condition of NP greater than 5 or NQ greater than 5. If this condition not met, and this is a situation where you cannot apply population proportion. Conversely, we will have one more situation called case 2, when sample size is sufficiently large, such as NP greater than 5 and NQ greater than 5, then central limit theorem, it fulfills the central limit theorem, and the sampling distribution of sample proportion P, small p, is approximately normally distributed. So one thing is clear, in Ztest you may see the normality condition, or else you may see assumption of Ztest where your test must meet the normality condition. So this is very important. You have to check this before you proceeding to testing a hypothesis. So in the case 2 situation, you can move further for testing hypothesis that NP greater than 5 or NQ greater than 5. Then you can move further. If your case is 1, you cannot move further. Then let us have a problem for testing a hypothesis under population proportion. So in this problem, a machine produces a large number of items, out of which 25% are found to be defective. So 25% of the total production by the machine A or some machine are defective. Now the company manager wants to check this. For that, he takes a random sample of 100 items and found 35 items are defective out of 100 items. So now what we want to do is there any evidence of more deterioration of quality at 5% level of significance? So here very simple, there is a machine in a company which produces a large number of items, out of which 25% are found to be defective. Company manager wants to check this whether really 25% are defective out of all the production by the machine. For that, he takes 100 sample and found 35 items are defective. Now we want to check, is there any evidence of more deterioration of quality at 5% level of significance. Then let us attempt this very systematically. As I told you already, you want to think whether we can apply population proportion for this problem, because as I said you, if you want to apply the population proportion for your testing hypothesis, the nature of problem, in the problem you can divide the whole attribute as two categories. Example, male, female, defective, non-defective, like that. If you observe in this problem, a machine produces a large number of items, out of which 25% are found to be defective, which means 25% are defective and the remaining 75% are non-defective. So in this problem, you can divide the whole attribute as defective items and non-defective items. So this is a perfect situation where you can apply population proportion. So now we have decided we can apply population proportion for this problem based on the nature of this problem. Then let us define the success or failure, that whatever we are getting defective or non-defective, like that. Before that, I will derive some of the information from the problem. Look at the problem. A machine produces a large number of items, out of which 25% are found to be defective. So this is very important consideration. This is a population proportion. Why? Because in the lifetime of a machine, particular machine production, 25% are found to be defective. So we are considering whole production of a particular machine. So which is the population proportion. So let P, caps P, can be denoted as population proportion of defective items, that is 0.25. So we want to convert this to the 100. So 25 by 100 is 0.25. Now we are having sample proportion. Now we want to have population proportion we are having now. Now we want to have a sample proportion. Sample proportion can be denoted by small p. Very carefully you have to observe, because we want to apply this to the formula. Look into the second sentence to check this, which means 25% are really defective. A company manager takes a sample of 100 items and found 35% items are defective, which means this defective items came from the sample taken by the manager. So out of 100 sample, 35 items are defective, which means small p is a sample proportion, which is a observed proportion of defective items in the sample, which is 35 by 100 is equal to 0.35. So one thing is clear. We found two things. One is population proportion, one more is sample proportion. Population proportion is 0.25, and now we want to derive other information along with caps P and small p. So we have caps P, which means population proportion as 0.25. Also we have small p, that's a sample proportion as 0.35. So along with that, we also want to have Q. So you will come to know in the formula what are the requirements in the formula. I will show you the formula later. So we want Q now. To obtain Q, you know already that you obtained P, that's cap P. If you know very well in the probability, you will come to know this thing, that is if 25% are defective and remaining 75% must be a non-defective items. So here defective is a success and non-defective is a failure. So defective can be taken as P and non-defective can be taken as Q. So if you want to get a Q, you want to subtract 1 by P, because we are dealing with probability. So if you subtract 1 by P, you will get a Q. So 1 minus 0.25, because P is a 0.25. Now your Q is 0.75. And along with that, a manager taken a sample of hundreds items to check whether it is a true. So in this case, N is equal to 100. Sample size is 100. So also we have alpha. Here there is alpha of 5% level of significance. Alpha is 0.05. So with this information we can apply it to the formula. So we have here caps P, small p, caps Q, N and alpha. So now let us set up a null and alternative hypothesis. Then here I have copied the same problem. So here we want to test that machine produces more defective items, that is a proportion of defective items, that is caps P is greater than 0.25. So our claim is P greater than 0.25. If you want to know how we are getting this, for claim we will get a the claim from population. So in the population, the whole machine produces a large number of items, out of it 25% are found to be defective, which means which is a claim. And in the problem itself, they have asked, is there any evidence of more deterioration of quality? They are asking, is there any evidence of more deterioration? So our claim is P is greater than 0.25, which means a machine produces more than 25% of defective items. Then its complement would be P is lesser than or equal to 0.25. When we say there is a more than 25, it can't be less than of that. So P is, the complement will be lesser than or equal to 0.25. So here observe here since complement contains equality sign, we will take null hypothesis as complement, that is P is lesser than or equal to 0.25. So that mean indicates proportion of defective items lesser than 0.25, and claim as alternative hypothesis, that is a P is greater than 0.25. That means proportion of defective items are greater than 0.25. So now we set up null and alternative hypothesis. Now let us also we have here a significance level, that 0.05. Also we have sample size of 100, which is not a case of t-test, which must be a z-test. So appropriate test for this problem is z population proportion. So now we have to check normality condition before we going to testing a hypothesis. The normality condition, as I told you, NP and NQ must be greater than the 5, then normality condition met. So here in this example, our N sample size is 100 and P is a sample proportion, that is a sample proportion out of the manager taken 100 sample, out of which 35% are defective. So sample proportion is 0.35. So 100 into 0.35, which would be 35. 35 is a greater than 5. So NP normality condition met. Then let us see NQ normality condition. So as we see, N is a sample size, N and Q, as I told you, we will obtain by Q by 1 by P. Here small p, 1 by P. So 1 and P is 0.35, 1 by 1 minus P. Then Q value we obtain 0.65, 100 into 0.65, 65. 65 is also greater than 5. So in NQ and NP, we met the NP and NQ are greater than 5. Since it is greater than 5, sample size is sufficiently very large, which means NP is greater than 5 and NQ is also greater than 5. So we see that a normality condition meets. Now we can go for Z-test. So very importantly, the formula we will use to test Z-test for population proportion is Z is equal to small p minus big P in the square root caps P and caps Q by N. So here all the relevant information we have gathered here when we extracted from the problem, that's caps P, small p, Q, N and alpha also. Now directly we can apply to the formula. Here in the right side I have applied to the problem formula. So small p, our small p, which means sample proportion is 0.35 minus our population proportion is 0.25, and in the square root our population proportion is 0.25 and our Q, we obtained Q, that is population proportion non-defective as a Q denoted by Q, which is a 0.75, and our sample size is 100 in this case, so 100. We have applied all the information to the formula. Now we have to simplify this problem. Then we will obtain the result. So 0.35 minus 0.25, that's a 0.10, and 0.25 into 0.75 divided by 100 and take a root of the value, it will give 0.0433. So now our tested statistics, when you divide the 0.10 by 0.0433, it would be Z is equal to 2.31. Now we will obtain critical region. To obtain critical region, we have to decide whether it's a two-tailed test or one-tailed test. To decide two-tailed or one-tailed test, you have to concentrate on the hypothesis. In the hypothesis, we have to concentrate on alternative hypothesis. Let us see what is alternative hypothesis so that we can decide whether it is a two-tailed or one-tailed. So here we have our hypothesis. Since our alternative hypothesis is a right-tailed, which means one-tailed, that's a right side, which means greater than. Since it is a right-tailed, our tested, this is a problem of right-tailed test. Since our test the statistics is a right-tailed, so rejection falls in the right side of the sample distribution. For that, we have to obtain critical values from the Ztest. Our alpha significance level is 0.05 and our test is right-tailed. So at 0.05 alpha for right-tailed test, Z values would be 1.645. The critical value is marked here, that a blue shaded area is a critical value 1 and in the moving further 1.645. And this red shaded area is a tested value. Our tested value is 2.31. So tested value is here, red shaded area 2.31. Since all the area from the critical value onwards will be rejection region. The region which is shaded is a rejection region. So since our tested value is 2.31 and our tested value is 2.31 and our critical value is 1.645, our tested value is falling within the critical region, that's in the rejection region. Since tested value is falling in the rejection region, we have to reject this hypothesis. So here our right-tailed test, so the critical values, as I said you, at 1% level of significance is 1.645. Our tested value is greater than critical value. So 2.31 is greater than 1.645 from the half side to positive infinity, and that tested value fall within the rejection region. Also we can take decision based on p value. Our alpha in this case is 0.05 for the level of significance and p value is 0.0104. Even when you compare with the p value also, our alpha is greater than p value. Actually, if you want to accept the null hypothesis, p value must be greater than alpha, but here it is the opposite case. Here alpha is greater than p value. So this is a case we are unable to support our claim at 5% level of significance. So after evaluating two alternatives using p value and critical value, we are going to reject the null hypothesis. There is no sufficient evidence to support our claim. Thank you so much for watching. Please do subscribe to my Vision Academy YouTube channel.